With that, I'd love to introduce our next speaker, who is the indomitable Professor Maria Emelianenko in our mathematics department here at George Mason University. And she has kind of single-handedly kicked off all of Mason's efforts in quantum algorithms and is just, a gifted science communicator and is a even more gifted researcher. And should I do more praise, Maria? Is that
Please
sufficient?
don't.
Okay, very good, very good. But I will be back on later. Thank you, everybody, for your time. And Maria, please take it away.
Great. Well, thank you so much, Patrick, for the introduction. It's going to be hard to live up to the expectations that you set up for me. So let me just introduce myself. I am a mathematician. I've been at Mason for 13 years. I'm applied and interdisciplinary mathematician working on modeling, simulation, and algorithms for a while. And quantum computing is something that is a recent interest of mine. The goal for me today, as a person who represents quantum computing group in the center, is to talk to you about basic principles and just give you a glimpse of what quantum computing really is, and then talk about some of our efforts and advertise some of the talks that you will hear later today. But before I do, let me ask Van Gu, is my slide visible?
Yes.
Okay, all right. So please let me know if something is off, if you cannot hear, or any other glitches. Hopefully nothing like this will happen. Okay. So let me just start with a little story. Back in the early 2000s, I was in graduate school at Penn State University, and I was part of this program, which was called High Performance Computing Minor, which was a very revolutionary thing at the time, and it involved students from a variety of disciplines, including mathematics, including computer science, including physics, from around campus. And this is where I learned about Moore's law that maybe most of you already are familiar with. And at the time, it was really, when we were learning about it, it was clear that the law really was corresponding to the data that was collected at the time. And although it was predicted back in 1965, this trend that Moore postulated, which said that the number of transistors on a computer chip is doubling every 18 to 24 months, really corresponded well with all of the predictions at the time. But it was also clear that if we continue at that pace, eventually we will hit a point where things would not be possible to maintain at the same rate. And when we kick nanometer scale, different physics and different mechanisms and different laws will start kicking in. So the talk, even at that time, was what do we do? So should we think about a new technology? What happens if this Moore's law is slows down eventually? But there were no particular answers to that question, or at least in the community of people who were talking about it, it was questionable that we can do much about this in the next few years. However, the data, the size of the data is increasing dramatically. And as you know, it's very difficult for computing resources to keep up with the growth of that data. And so there is a huge push to really understand how we can handle all of these, all of the challenges in this big data realm, and try to come up with algorithms, but also with computing resources that are able to address it. So quantum computing really kicked off in the last decade or so. And I'm showing you here the growth, which is really interesting if you think about it. So it all originated with Feynman back in the 60s, who said that, I think this quote is actually from the 86, where he said that really, if you want to model nature, which is not classical, then you actually have to take into account quantum mechanical laws and build the computer based on the quantum mechanics. So Patrick already explained a lot of these ideas, and I will go over some of them again. But what you see is that the technology was really not there for a while. So some of the early attempts at building a computer with qubit technology was in '98, then in 2000s, there were successes with 5 and 7 qubits, and then it kind of stagnated for a while. So between 2008 and 2016, we see that a lot of effort has been put into it, and suddenly there is a huge bump in the productivity, and the success rate is amazing in the last couple of years. That's why there's so much funding that goes into this. There's a lot of technological advances happening. And this trend seems to be set to continue. So there are more and more systems that are becoming available. So some of the key players are listed here: IBM, Google, and Rigetti. But at the end of the day, what are we gaining, and what is the underlying mechanism? So why is quantum computer so different? So it's probably an impossible task to explain it in full in the 15-minute time that I'm allocated. But roughly speaking, you can think about this as instead of bits that you're used to in the classical computation, which correspond to the 0 and 1, and that's depicted here in this cartoonish way that you flip a switch and it becomes 0, 1. So all of the information is encoded in this way in the classical computer. Now, if we use the quantum technology, suddenly you are able to use this probabilistic setting where you can be at the same time in a variety of different states. So the superposition principle, one of the key principles in quantum mechanics, is telling us that you're able to be at the same time in multiple states. And that really increases your computational power dramatically. So instead of just flipping a switch and or flipping a coin and having a head or tails, you are able to really, when you are inside the quantum system, you can position yourself in any of those states at the same time. Entanglement is another key aspect that Patrick talked about, but pictorially, what you can think about is if you are doing permutations. So if you have an n-bit representation of a number, you can only be in one of those positions, one of those possible 2 to the n permutations at a time. So this has been the mechanism that we have used in the classical computing for a while. But now, because of this superposition principle, when we're talking about the qubit representation, and we have n such qubits available, we can really view all of these 2 to the n possible permutations simultaneously. So this is, again, recapitulating the point that I was making in the previous slide. So why is it good, and what is the benefit? Imagine the quantum computer that has all of these n qubits, and I told you the story that technologically all of these advances are happening that allow us to push for more and more qubits to become available for realistic applications in the next decade or so. We have this quantum computer that operates with all of these quantum technology. And then the set of gates that we attach to each of the qubits, these are the operations that act on all of these qubits 1 at a time or 2 at a time. And at the end of the day, you are measuring the results. So this is the readout. And remember, in the Patrick's presentation, he did talk about the fact that when you're measuring, you're really destroying all of these wonderful quantum properties that allowing us to gain the advantage over the classical architecture. So this is kind of roughly what we're dealing with. So we would like to build algorithms and utilize the technology so that we can maximize the impact and try to speed up the applications as much as we can. Some of the other effects that are really cool that are coming from quantum mechanical perspective are the quantum tunneling effect. And I'm depicting here this image, which probably is familiar to people who have ever done optimization. So you're looking for the global solution, maybe the global minimum. And instead of going around and going up and down these hills and valleys, if you're able to utilize quantum terminology and put it in the form of a Hamiltonian, for instance, you can use the quantum tunneling effect that allows to kind of bridge through and go across from one minimum to another. So all of these things are very kind of crude explanations, but they are allowing and enabling huge advances in terms of algorithmic speedups. So let me just mention a few of them and just tell you the story that, in fact, not all of the applications are amenable to quantum speedup. And there are different types of speedups that are available because, in fact, you have to really prove whether or not all existing classical algorithms are performing substantially slower, and you have to prove rigorous bounds on the complexity of those algorithms. But there are situations when people have been able to show that indeed exponential speedup is achieved. For instance, Shor's algorithm. So this is the algorithm that has been known for a while. And what it does, it's allowing to factor a d-digit number. So this is a prime factorization problem that Patrick alluded to that is really important for encryption and security applications. It's known and proven that the Shor's algorithm complexity is proportional to d to cube, where d is the number of the digits of the number, whereas in the classical algorithm, the best known algorithm is of complexity exponential of d to 1/3. So you see right away that there's in this graph, there is a logarithmic scale on the y-axis, and the digits are marked. On the x-axis, you can see a huge advantage that the quantum realization of this algorithm is able to achieve. In fact, if you think about how long it will take you to factor a number with 250 digits. So right now there's not even it's not even possible in current classical computation. And if you're thinking about increasing that to 300 and more, it will take you to the end of your lifetime and the lifetime of your kids. And in fact, none of the available classical computers are able to do that. So this is one of the examples. Other problems, for instance, Grover's search, which is a problem of finding a value. So if you have a function f of x, and it's a discrete problem, so you basically have a mapping from x to y, and you're looking for the value that delivers a certain desired value of y. This search which is called the Grover search algorithm, is speeding up the classical alternative in a polynomial way. So this is what is called a polynomial speedup. So it's not as dramatic as the speedup of the Shor's algorithm, but it nevertheless is really, really important and is used in a variety of applications. And still, you can see a huge advantage that it brings to in terms of the number of evaluations of the function. So these are just two examples. And of course, what is important and what is really the target in some of the research that is taking place in this domain is to find the problems that can have an exponential speed up in its quantum realization. And it also is pushing the classical algorithms to become better because we're competing now with the quantum technology. One example that maybe is something that you might find intuitive is a quantum random walk problem. So Here, it's a very specific problem with a very specific setup that was proven to have an exponential advantage over the classical walk. So what is the interesting piece here is that if you are walking from left to right, from the entrance to the exit of the walk, and if you are in a classical setting, you basically have two options, go left or right. So you don't really have ability to look around and explore all the other directions. So the classical walker in this setting will need exponential time to get from the entrance to the exit. And so for the column in the middle of this glued tree graph, you have 2 to the n vertices. So that's really what that limits your ability to decrease the time that it will take for you to complete the walk. The quantum walker, on the other hand, when it gets to the middle of this graph, has ability to choose all of these directions simultaneously. And that really is a huge advantage, which brings down the complexity and allows to complete the walk in linear time. So this you might say, okay, this is a very specific and artificially constructed example. Yes, it's true, but some of these ideas have been actually instrumental in putting together very important realistic codes and algorithms for solving problems that have to do with the quantum structure of matter, with simulating chemical processes, biological processes, and a lot of work is taking place, which is really theoretical, but also computational, and advances are being made every day. So what are some of the pitfalls here? If you look at this image, you will see that we're kind of in the beginning of this big quantum revolution that Patrick alluded to. We're currently not able to run realistic simulations, which are large-scale simulations, due to the fact that we have error that propagates in all of the quantum devices. So this noise intermediate scale quantum computing error, which is called NISC, is predicted to last possibly about 5 to 10 years. And then we're hoping that we can actually reach this fault-tolerant quantum computing stage where we will be able to really scale some of these ideas up. The costs are there, and it's not for free. But if we're able to break through, and if we're able to continue making advances in terms of the algorithmic performance as well as correcting the error of the quantum gates, sky is the limit in terms of the applications. Again, I'm stressing that not all of the problems will necessarily benefit from quantum speedup, but problems that exist in these domains, particularly those that have to do with optimization or scheduling or factorization of numbers, like in the cryptography. But also, you can think about a variety of different artificial intelligence tasks that you will hear about later today that can be and are already being implemented in a quantum computer. Some of these technologies will benefit dramatically from the quantum speed up. So I will, I'm running out of time. So I will just mention that we have a group here at Mason that consists of faculty from math, physics, computer science, and we're working with industrial partners. We have very fruitful collaborations with Buzão and Hamilton, as well as Mosaic ATM, and we're working with partners in Portugal on some of the algorithms. We're mentoring students, and we're looking for additional members to some of the projects that we're currently running. So you will actually hear from Javier and from Ian later today, and I believe that Connor will also talk later about his work. And this is just to mention some of the partnerships and the fact that we participate in international and regional conferences. And this is just a picture for one of the projects that we currently have, and it's very cool. It's about optimizing the flight trajectories for manned and unmanned air vehicles. So this is a project that we have joined with Mosaic ATM. So the goal here is to use quantum computing techniques to allow the unmanned vehicles to choose the optimal path. So you see here, this is a domain, a terrain with some features, and the quantum technology can be really instrumental and believed to have great promise in terms of optimizing the decision-making at each of these waypoints of the trajectory. So what they're talking about is really revolutionize the transportation industry and allow people to travel not on the roads, but using these little unmanned helicopters from point A to point B. And this is coming up in the near future. So this is the kind of the rough summary. The research areas that we work on have to do with machine learning, optimal pathfinding, approximation optimization algorithms, scheduling, data sketching, and more. And we do have positions available, so please talk to us if you have interest in joining the team. And we're also looking for collaborators, always to work on joint proposals and such. So I will leave you with the contact information, and I think I'm out of time, so I will just stay around. If you have questions, please put them in the chat, and I will let my colleagues take over. So I think Jessica Rosenberg and Ming Tian will talk to you now about the master's program that we're developing, and also about the courses that are being taught at Mason that have to do with quantum computing. Thank you.